speaker is Jocelyn Bell, who will tell us about kappa proximal space.
Okay, well, thanks everyone, and thanks to the organizers. So, as the first speaker today, I'd like to go ahead and set the bar pretty low. Alright, so first of all of my spaces today will be Hausdorff, and actually probably a little bit more than that. And by more than Hausdorff, I mean they'll have a structure on them called a uniform structure, which just really quickly to give you an idea of how this works is a uniformity is a collection of subsets of the square of a space that satisfies some certain properties, and an element of uniformity is known as an entourage of the diagonal. So here's a picture. That's supposed to be a picture of a square of a space, so x cross x. So that would be the diagonal then. And so you can picture an entourage as simply a set that contains a diagonal of x. All right. And what we can do with these is we can use these entourages to create subsets of the set x by fixing a point x1 in the space and then collecting all the points whose second coordinate lies in D and whose first coordinate is x1. So just like this picture, so the magenta strip on the side is the D ball about x1. So you can do this for a different point, so if x2 is there, then you'll get the purple strip, which is the D ball about x2. And sometimes I'll draw pictures that look like this. So on the left, I have a picture of an entourage there. So we're pretending x is one-dimensional. And then on the right, x is two-dimensional, so you can see what the different D balls for different points x in the space might look like. So what do? We do uniformities generate topologies. How do they do that? Well, a set is open in something called a uniform topology if for every point in that set you can squeeze a D-ball around it, completely contained inside the set that you're claiming is open. So a set together with a uniform structure on it, this blackboard gold D, is called a uniform space, and the topology on X is the uniform topology. All right, so the title of my talk is Kappa proximal spaces, but before I tell you what a kappa proximal space is, I'm going to tell you first what a proximal space is, and then kappa proximal spaces will be more general than proximal spaces. So first of all, we learned this morning that games are fun, so here we go. The proximal space is actually defined in terms of an infinite game. And here's how you play. So here's my space X, it's a gray square, and there's two players, entourage and point. And entourage is going to choose entourages, and point is going to choose points. Okay, there we go. So let's say entourage moves first and chooses some entourage D1. So again, I'm mixing up that's supposed to be a picture of something in the square of X cross X, but I was a little lazy with the labels on that. And then it's point's turn, and he'll just choose any old point in the space. So let's say he chooses x1 and it happens to be there. All right, now it's entourage's move again, and she'll choose a potentially different entourage. And now point is restricted in what he's allowed to choose. He has to choose from the D1 ball about x1. So this is where the color coding comes in handy, because it's not the D2 ball about x1, it's the D1 ball about x1. So he has to choose from there, so let's say maybe x2 is over there, and so on. So then entourage moves again, chooses some D3, and now point is stuck in the D2 ball of x2, his last choice, right? So not the D2 ball about x1, but the D2 ball about x2, and has to choose something from there. All right, and then so on, D4, I didn't bother to draw a picture of that, and point responds with an x4 in the D3 ball about x3. Okay, so in the end, after we play this game, we're going to say that entourage is the winner if one of two things happen. So she has two ways to win. The first way is if the sequence of points that was chosen by the player point converges, or if the intersection of all the D balls created along the way is empty. So entourage has two ways to win, and if neither of those happens, then we'll say that point wins. All right. So a uniform space is proximal if entourage has a winning strategy in the game that I just described. And an easy example of a proximal space is a space, where you want to think of what entourage is really doing is choosing radii that are getting smaller and smaller and smaller, and so the neighborhoods are shrinking down. All right? But there are proximal spaces which are not metrizable, and here's one example. So the one-point compactification of an uncountable discrete space happens to be a proximal space that is not metrizable. All right, so these proximal spaces have already on them a uniform structure, which makes the topology T3.5 already. If you have this winning strategy for entourage, then you can show a little bit more. So proximal spaces are collection-wise normal and countably paracompact. And what I'm going to talk about today are these kappa proximal spaces, which are more general than these. So they we might have to sacrifice something here, and they'll satisfy weaker properties. So let's see. All right, so here let's define a kappa proximal space. It's going to use a game just like the proximal one. And it's very similar, so this will be quick. We start with a uniform space, but what's different here is I first fix a subset K of my space X, and then we're going to play the same game we just played, except we'll put an additional restriction on point that he's only allowed to choose from the set K. So obviously this game depends on K, so I'll call this the K proximal game. All right. So just to remind you how this goes, here's the space. All right. What's different now in this K proximal game is that there's my subset K, which I've drawn as this sort of smattering of points. Entourage will move first and choose her neighborhood of the diagonal, and then point has to choose from one of those yellow dots. So that's essentially the difference here. Entourage moves again, chooses a D2. So the rules are the same here. Point is still stuck in the D1 ball about X1, but he has to choose a yellow point that's in the blue circle. So maybe he chooses those two, which is over there. And so on. Entourage chooses D3, and then point is stuck in the D2 ball about X2, but also stuck in K. So has to choose something maybe like that. All right, and so the winning criteria is the same. So entourage again has two ways to win. Either the sequence converges, the sequence chosen by point, or the intersection of the D balls created along the way is empty. And I put here in parentheses converges in X and intersection is empty in X, because I'm trying to emphasize this is not the same thing as playing the proximal game in the subspace K. All right. And if neither of these two things happens, then we'll say that point wins. All right, so here's how we can define a kappa proximal space. So if you just take a look at the K proximal game for every subset K of X, a cardinality at most kappa, and if entourage can always win, then that's what we're going to call a kappa proximal space. So here's a quick example of something that's a kappa proximal space. So it's kind of like one-point compactification of an uncountable discrete space, except with one difference. We'll start with a discrete space. Well, here kappa is supposed to be a cardinal. Take a discrete space and cardinality at least kappa plus and add a point at infinity, and let subsets of X be open, and an open neighborhood of infinity looks like the complement of a set that has cardinality at most kappa. And it turns out that this space is kappa proximal but not kappa plus proximal. And in the unlikely event I have time, and I'll go back and do these details, but of this example. Instead of doing that, though, I want to talk more about the results that I have for these spaces. So, kappa proximal spaces, what can we say? Well, I said that proximal spaces, for example, are normal. This kappa proximal property is weaker. So spoiler alert, there are kappa proximal spaces that are not normal. So what can I show? Well, I can show a weak form of normality called pseudo-normality. So in the case, well, where we have omega proximal means alpha not proximal, but it's easier to say omega. So omega proximal space. And pseudo-normal just means that you can separate two disjoint closed sets provided at least one of them is countable. So a weaker form of normality. All right. So what I'd like to do is sort of give you some reasoning as to why this should be so. So let's start with a space that is omega proximal, so Entourage has this winning strategy for every subset K of X whose cardinality is at most countable. And because this is a proof sketch, I need to make a simplifying assumption, and that will be this. So the uniformity has this particular kind of base, where if I collect all the D balls for pick an element in that base, collect all the D balls, that actually partitions the set X into clopen sets. So this makes the uniform topology on X zero-dimensional, but it also makes for some really nice pictures in the sketch. All right, and here's the sort of the outline of the proof. Here's the plan. So I'll start with a countable closed subset of X, which I'll call K. And then I'll put K inside an open set G. And the idea is to find a clopen set H between K and G. So here's a picture. So the gray square is the whole space. The blue circle, or oval, I guess, is K. And then the wiggly thing around it is G. Okay. So here's the plan. K is countable, so I can enumerate it. And what I'm going to do is, well, the space X is omega proximal, and K is at most countable, so I know there's a winning strategy for Entourage in the K proximal game. So I'll call that strategy X, so S for strategy. And the idea is to define a very nice descending sequence of entourages, which are elements of the special base. So D1 containing D2 containing D3. All right. So let's go ahead and start by defining D1. This is an easy one. So that's my set K is contained in G. So K1 is somewhere in there, so that means G is open. I can choose an element of my base so that the D1 ball above K1 is completely contained in G. So that's how we'll choose D1. All right. And now what I'm going to do is create something which you can consider as sort of a level 1 cover of K. And you take the D1 that you just chose, and then consider all the D1 balls about X, where X is in K. And because of the simplifying assumption, so this is just a pairwise disjoint collection of clopen sets which covers K. So here's a picture. So it turns out in this picture I only have 3 elements in my level 1 cover. I have A1, A2, and A3. All right. And then what I'm going to do is divide up each one of those. So let's see how to do that. So for each A in the level 1 cover, first what I need to do is I need to choose a designated representative from K. So I'll call that little k sub A. So this is all I need, right? So each one of those, A1, A2, A3, has non-empty intersection with K, so I'm just going to pick something there and call it K sub A. All right. And this is a cover of K, and we enumerated capital K is K1, K2, and so on. So K2 is sitting somewhere. I don't know where it is, maybe it's there. So there is an element of the L1 cover that contains K2. So here's how we're going to choose D2. We're going to choose D2 so that it's contained in D1. Also is an element of that special base. We choose it so that the D2 ball about K2 is in the element of the level 1 cover that contains K2. And also so that the D2 ball about K2 is contained in G. So in the picture it might look something like this. The one thing you can't see in this picture is that D2 is contained in D1. So that's we're finding the D1 cover of X. Okay, so now we're going to define our level 2 cover. So we'll start with any element of the level 1 cover. So here again is the level 1 cover. It has 3 things in it. So let's say we picked that one over there, we picked A3. Here's how we're going to divide up A3. First, we remember that we chose a distinguished representative from the closed set K in A3. And then we remember that we have a winning strategy for Entourage, and we've just seen a point. So we can take the strategy that Entourage, the Entourage chosen from Entourage seeing the point KA3, so that's that S of KA3. And then we're also going to take an Entourage which is contained in D2. And then what we're going to do is we're going to divide up A3 into the level 2 restricted to A3, so like that L2 superscript A3. So in that case, it's just going to give me a B1 and a B2. So that divides up A3, and I only collect the things that divide up A3 that happen to intersect K. Okay, so here's this is the text for everything that I just said. So you do this for each A in your level 1 cover. And then after you've chosen that use of A, which is an entourage, you use that to divide up the set A. And then what you do is you collect all of those for all the A's that were in L1. So here's a picture, all right? There's my level 1 cover, maybe my level 2 cover looks something like this. So now it has 6 things in it. And it's a refinement of the level 1 cover. All right. So we're going to do the same thing. We're going to need to choose a distinguished representative for each one of these elements of the level 2 cover. So that's what these things are, the KB2, KB5, and so on, elements of K. And this is a covering of K, so there's some element which contains K3, where K3 is the third element of my original closed set K, so maybe K3 is over there in B3. All right, and since, here's how we're going to choose D3, so we choose D3 inside of D2, and then those other two conditions are very similar to how we chose D2. So here's sort of the picture, right? So now it's on the side there. So you choose a D3, K3 contained in something like that, so it's also contained in the gray because it's contained in G. All right, and then we'll define our level 3 cover. So here's the level 2 cover. We're going to do this for every element of the level 2 cover, pick one. So let's say we pick B2. All right, there's our distinguished element of K from B2 that we chose earlier. But we also know that B2 is containing exactly one element of the level 1 cover, which is denoted by A3. So we have those 2 points there, KA3 and KB2. So if you can see it way at the top, we're going to choose an entourage that is smaller than the strategy that you get for KA3. So now we're just in probably the land of too many subscripts where that's getting hard to read, but the idea is we're going to chop up B2 using the winning strategy. And we're also going to make sure that we have a refinement of the level 2 cover and also a refinement of the D3 that we chose. So when we divide up B2 like that, maybe we'll get a C1 and a C2. All right? And here's the text again, a big pile of text for everything that I just said. And we choose that specific entourage, we divide up B, and then we do that for each B and union them all together. So the general picture is this. You start with your level 1 cover, proceed to your level 2 cover, and then maybe your level 3 cover. So it refines L2, and so on. So that's the construction, all right? What we did was we created this nested sequence of entourages D1, D2, D3 that satisfies the D eyeball of Ki is contained in G. And we also defined these covers, these level n plus 1 covers of K that do these points that I've written up there, 2 and 3. So the way that the proof proceeds, which goes very quickly, because it's supposed to finish in 2 minutes, is that you can actually show that this union is closed. These, the D balls, the D n dot K n balls, which take all those together. That's actually a closed set. And so that is the Clopin set then that we were trying to find, where we were trying to squeeze a Clopin set around K that was contained in G. So this will do it. So just really quickly here, if there is an n where y isn't in the nth level that you created, then it's easy to show that y is actually in the dj ball about kj for some j. So suppose that doesn't happen, and for every n, y is in some element of the level n cover that we've created. So what that means is that y is in the level n cover for each n, so you can pick exactly one element of the pairwise disjoint. So you can pick exactly one element, the one that contains y, and that's going to give you a descending sequence of sets where y is in each one of them. And you have these representatives that are this k sub qi, which are elements of K that were chosen for each I. And then along the way, we've also been using this winning strategy for entourage. So again, there's a lot of text up there, but the basic idea is this was constructed carefully enough so that point is actually playing by the rules of the proximal game here, the K proximal game. And by construction, what we've shown is that y is actually in the intersection of all the balls created along the way with the proximal game. So that intersection is not empty. And what that does is that takes away the second way for Entourage to win. There were two ways. So it's not the second way, which means it's the first way. And the first way says that the sequence of points chosen by point has to converge. So now the idea is that is a KQ1, KQ2, and so on. It's a sequence of points in a closed set, so it converges to something in that set itself. And we had enumerated K way back in the beginning, so let's say that sequence converges to K sub J. And then eventually what we're going to wind up showing is that Y is in the DJ neighborhood of KJ. And one of the key facts here is because the LM, the mth level that we created, refines that partition of X. And so, again, here's a bunch of text, but what happens in the end is that Y is in the DJ ball about KJ, which means that that union is closed because that was a point in the closure, and so we were just showing that it was a point in the set. Okay, so just really quickly, one other thing I can show is this. So a sigma product of omega proximal spaces is omega proximal, where a sigma product is just a little bit more general than an countable product of spaces. So this means that a sigma product of omega proximal spaces is pseudonormal. And one more little thing is that, so something is omega bounded if every countable set has compact closure. So a locally metrizable uniform space that's omega bounded is omega proximal. So what kinds of objects are these? Well, any topological manifold is a locally metrizable uniform space. So if you had an omega bounded one of those, then it would be omega proximal, which also would mean that it is pseudonormal. And there are actually topological manifolds which are not pseudonormal. So I think Peter wrote about that. So you can go ask him for some examples there, right? So there is, what I'm saying is, there is something to show here. So here's an example of an omega bounded topological manifold. So the long ray looks like the long line. And so we can say that a sigma product of long rays is pseudonormal, which, to my knowledge, this was previously unknown. So it's something to do with these results. All right, so I'm sorry I went 2 minutes over.
So you said that all proximal spaces are normal.
Yes.
Is there any sort of converse? Like, does every normal space have a compatible uniformity that makes it proximal?
Oh yeah, no, that doesn't work.
No.
I should know that. I know that there's an easy example, but I can't think of it right now.
A non-coarse and compact space.
See?
Okay, any other questions?
So omega bounded implies pseudonormal. Does omega proximal implies pseudonormal? Would kappa proximal imply the kappa version of pseudonormal?
So the problem is the proof, the game isn't long enough. The game is countable length, right? So I don't know. I would have to do something where the game were allowed to extend to kappa in order to create, or at least the way, I don't know, maybe I have a better idea. The way the proof goes, I really need countable for that. So I don't know the answer to that question.
I was basically along the same lines, wondering whether or not higher degrees of proximal basically correspond to some generalized sort of between pseudonormal and normal? Like,
yeah, no, that's a great question.
Yeah,
yeah,
okay.
so, I mean, this is new. I mean, this is newer stuff for me, so
Okay.
I'm looking for things to go on from here, and that's a great direction. Yeah.
Any other questions? All right, let's thank the speaker again. Next time, we got 5 minutes.
That was the one where we were about to go to dinner and we made it.
Our next speaker is Christopher Paragona from the University of North Texas, and he will tell us about an extension of the Bear property.
All right, thanks to the organizers for wanting me to speak. So here's the outline. I'm going to just go over some preliminaries, basic definitions that we should all be familiar with. I'll give the core definition of a sigma ideal that will be of interest, which will give rise to the extended Bear property. And then I'll talk about relationships with Martin's axiom and future work. So, of course, Polish space is a separable, complete metrizable space. Good. And we define meager. So, meager. Or first category, as some people like to call it. Right, so these are the small sets, as it were, in terms of category. Okay, so let's build up some of the other players. So this script M of x is going to be my collection of Borel probability measures on some Polish x. Of course, I can make that space Polish as well in the weak topology. Right, so Polish, therefore Bear, therefore category gives me non-trivial information. Okay, so we'll see. So it is a Polish space. Okay, sigma ideal, of course, so something which is closed under subset and countable unions. So the meager sets are sigma ideal, just by construction. And the Bear category theorem is much celebrated. It's just that it's a sigma ideal and it's proper. So if I have any Polish space, then it's not meager in itself. So, good. Now we're ready. Residual null sets then is what you may want it to be. So the outer measure is just the infimum over all of the measures of the open sets containing your set, usual outer measure. Right, so the measure space itself is a Polish space. Again, so I'm talking about category. So for any set A, I look at what I call the annihilator N of A to be all of the Borel probability measures which give it outer measure 0. And I'll say the set is residually null if that set is co-meager in the measure space, right? So most measures in the sense of category are giving me measure 0. Okay, and I'll denote the collection of all residually null sets by Rn. So in 1964, Dubbins and Friedman showed that. So they didn't isolate this notion. But they do talk about, they talk about the notion itself, although they didn't, again, isolate it and study it in isolation. They did it for the compact metrizable case, slightly simpler, but it's true in just general Polish spaces. All meager sets are residually null. Right, so this is maybe we're feeling the extension coming along. Also, if my set has the Bear property and is residually null, then it is also meager. So the sigma ideal meets the sigma ideal is the meager set in terms of just Bear property sets. Right, so many questions arise. Like, is this ideal different than the usual ideal? So in sets of, in universes, say, where I don't have full choice, then I might not have anything new, right? So residually null might not offer me any new sets, apart from just the regular meager. Okay. For example, like if all my sets have the Bear property. But if I have things like Martin's axiom, or just the continuum hypothesis, then I can build residually null sets which are non-meager. So in particular, I really just build universally null sets, which I'll define soon. But, so strange sets do exist, and I do get new sets, depending on sort of what things are holding. Okay, so and we have the continuous or non-atomic measures, right? So these are the measures that give singleton sets measure 0, or just finite sets measure 0. Countable sets. So I'm only going to be interested in Polish spaces without isolated points. So you really will lose nothing if you just think that X is the reals throughout this entire time. And maybe you even want to be Bear space. Okay, so it turns out that the continuous measures is a density delta, in particular its omega itself. So if I define universally null to be all continuous measures give me measure 0. So not just a meter collection, but a very cometer collection, but a particular cometer collection. So if at least as long as I'm in a polar space without isolated points, then all universally null sets are residually null as well. So this is also an extension. But since we have the meager sets, they're not the same, right? I have residually null sets which are not universally null, in particular any perfect meager set, well, or any set with it, well, yeah. Because I want it to be residually null, and then it has to be meager. So I get residually null sets which are not universally null. So there's a right, so we have differences. So this is a much easier, so of course more overhead, but this is an easier form of the bare category theorem. In fact, the collection of residually null sets is a sigma ideal, and it's proper for the trivial reason that x always gets measured 1. So good. Great. So we have a question. So I've shown that residually null sets contain universally null sets and the meager sets. Is it the case then that the residually null sets are just unions of universally null with meager sets? Why might that be the case? I mean, so all the examples, so the examples that one usually would think of, besides meager sets, are perhaps maybe a Luzine set. If you've heard of this, it's the universally null set which is non-meager. And besides, let's see, sort of the standard, right, but it's universally null. So here's, what are the other examples? So I have one, turns out. So in general, the answer is going to be no. I actually get more sets. So I can't just write, so not every residually null set is going to be the union of a universally null set with a meager set. So let's see. And it's going to live inside the product space. So if you give me x and y, Polish spaces, again without isolated points. And if I can find a set which is universally null but non-meager, then, so call it A, then A cross Y is a residually null set, but cannot be written as a union of a meager set with a universally null set. So let's see. I'll offer a sketch of the proof. So the first lemma is that the set of all measures on the product, so that there exists just some strand that receives a measure bigger than or equal to epsilon, that's going to be a closed and nowhere dense set. So this is the same, the proof of this is the same as when you show that there exist continuous measures. I just replace point with strand. So this is so that's nice. And so here I utilize that and this fact. So if A is universally null, and I have some measure on the product, and if it gives A cross Y positive measure, then it has to give that positive measure on some strand. Okay, so it has to be distributed on some strand there. So using those two facts, then, whoops, A cross Y is residually null, right? I just combine the fact that epsilon is 1 over n, say. So it's residually null. Right. So the rest is just showing that it can't be written as a union, and that follows really just from the Kuratowski-Coulomb theorem. So I pick some universally null set which is non-meager. Then what we just showed, A cross Y then is universally null, residually null. Sorry. And if you give me any meager set, the complement of my A cross Y, if there's going to be some perfect set of the form x cross f inside that complement. And so that little strand, which of course is meager in the space, it still supports a continuous umbrella probability measure. So therefore it's not universally null. So there's our example. And I'll come to a question related to this construction later. So let's actually look at the extended bare property, as you may expect. It looks exactly like the definition of a set with the bare property, except now I've replaced meager with residually null. So, a set has the extended bare property if and only if its symmetric difference from some open set is residually null. And if I have a function from Polish x to, I guess, arbitrary topological y, it's EBP measurable if the preimage of any open set has the extended bare property. Right, so since all meager sets are residually null, then this is our extension. So so this contains all sets with the bare property. And in models of ZFC, where I have residually null but non-meager sets, then this is a proper extension. Okay, so I have sets with the extended bare property which are not bare property. Okay, we have these other notions. So maybe before to say that this is in a similar vein, I mean this is a sigma algebra of sets, right? So it's sort of a measure algebra in some sense. And there are these other notions. So we have universally measurable, just mu measurable with respect to all measures, and residually measurable if I'm measurable with respect to a co-meager collection of measures. So sort of similar to what was happening with the residually null, but now I just want measurability, and of course. All universally measurable sets are residually measurable with no assumption on isolated points. But also, there are residually measurable sets which are not universally measurable, maybe not so interesting. I mean, I just take some meager set, find some perfect meager set, get a continuous measure supported on just that meager set, and find a non-measurable subset of that set, and that set won't be universally measurable. But by the fact that it's meager, it's residually measurable, right? So it's measurable already by virtue of being measure zero with respect to a co-meager collection of measures. So again, a little bit different. All right, so what's the application of these measurability things? Okay, so let's see. So recall your Polish groups. A group with a Polish topology for which the group operations are continuous. And the celebrated theorem is that all bare measurable homomorphisms between Polish groups are continuous. So this holds here. Very easy adaptation of all the proofs. Relies on this extension of the Pettis theorem. And it's all very easy when we say it. So, let's see. This one. No laser. So we have these, so meager generates the bare property sets. Right? My residually null sets generate the sigma algebra of the extended bare property, and I've established that group homomorphisms that are measurable with respect to those sigma algebras are continuous. And I just, with the universally null, I want to include there to sort of show this connection to the universally measurable, right? But this is, well, so I don't think this has been answered yet, but I think this is the big question, are all universally measurable group homomorphisms continuous? So this is, at least, last I've checked, a lot of it has been done. So I think it's done for the abelian case, maybe even solvable, but I think it's still in full generality. It's open. So you can ask the natural question, are all residually measurable homomorphisms continuous? Hopefully they're intimately connected. Hopefully the answer is yes for both. So now let's see our connection with Martin's axiom. So I came to Martin's axiom through the venue of bare category theorem and its relationship with bare category. So I can state Martin's axiom in its topological incarnation as so. For any compact Hausdorff space with countable singularity, right, so the largest collection of pairwise disjoint open sets is countable, and I have my collection of meager sets, then what I want to assert with Martin's axiom is that the covering number of the meager ideal is at least continuum sized. So I have to put at least continuum because maybe my compact Hausdorff spaces are, with countable singularity, are really large, like 2 to the kappa for large kappa. Let's see. Yeah, right. I don't know how. Yeah. But anyway, so the covering number, of course, this means that I can't cover my space with less than continually many meager sets. So in particular for Polish spaces, Polish spaces embed into the Hilbert cube as G deltas, and you can rephrase compact Hausdorff. You can replace, you can maybe just talk about check complete spaces. So Polish spaces are some of those, and so they satisfy the conclusion of Martin's axiom. But even more so, kappa linked unions, so where kappa is less than continuum, kappa linked unions of meager sets are still meager, and kappa length unions of null sets are still null. So it's a little bit stronger than just the statement of Martin's axiom, at least in this context. So if I combine those two facts, then under Martin's axiom, kappa length unions of residually null sets are also residually null. Surely. So this may raise the question, is there a relationship? Does it go the other way? Well, so what do I mean? So let's see. So if I go into a broader context, I leave the Polish and I go to just compact Hausdorff spaces. You can talk about, so it's important to impose the regularity condition on the measures. So I just let m of x be the regular Borel probability measures. So not all measures have to be regular here. But if I look at the regular ones, they themselves form a compact metric space in a similar way as the usual measures. I just look at the weak topology there. So my notion of residually null extends naturally. And since it's compact Hausdorff, okay, there are also bare spaces. So on and so forth, so nothing becomes trivial. And so I have this statement, as you may expect. It looks like Martin's axiom. If I have any compact Hausdorff space with countable cellularity, and then I want to assert that the covering number of my residually null ideal is at least continuum. So it turns out that in the compact case, meager sets are still residually null by similar arguments. So it might be a little bit more difficult, but similar arguments work. So all meager sets in this more general context are still residually null. So this just on its face implies directly Martin's axiom, since the meager ideal is a subset of the residually null ideal. But does it work the other way? So I've been thinking about that for a while. I can't, there seems to be, it's not so easy to relate the covering numbers. Also, does the analog to the Kuratowski-Ulam theorem hold? This is surprising, I find it to be surprisingly difficult, considering it's so easy. Well, it's not so difficult in the meager case, or the category case. And earlier we constructed a subspace of a product, which can't be written as the union of a meager set with a universally null set. Can a similar construction, or maybe just any construction, work in general Polish spaces? Like, is the residually null ideal always strictly larger than that? Well, okay, as long as universally null non-meager sets exist, can always build something which is residually null but not the union of a meager set with a universally null set. And that's it for me.
Any questions? Okay, well, let's thank the speaker once again. Next talk in about 10 minutes. Our next speaker is Alan Dow. Title of his talk is Sigma Compact Density.
Thank you, Gary. Thanks very much. Okay, I see I accidentally deleted my title page, so there's no title. So jump right in with definitions. So I just want to give some definitions so I can introduce the question that we worked on, we being Istvan Juhas and myself. So these definitions are well known to most everybody, but a couple of them are not. So the density of a space, of course, is, we'll say its density is less or equal to kappa if there's a kappa, less or equal to kappa size subset of your space X whose closure is X, of course. And then the pi weight of X, least cardinality of a pi base. And you can say it like this: if tau is your family of open sets, plus meaning non-empty, so you have a family of non-empty open sets, and it's dense in the order structure, the non-empty open sets. So every non-empty open set contains a member of the pi base. Cellularity of a space is, we heard in the previous talk, the minimum cardinality of a pairwise disjoint family. I said it's strange here, I think, right? For every family of open sets, you can find a kappa size subfamily whose union as a closure contains the union of the previous family. That's a strange way of saying cellularity, but I put it this way because I thought I needed this form in a proof, but I'm not going to give that proof, so. The tightness of a space, right? So the tightness I want to mention because it motivates, for Van Mill, in fact, Van Mill asked the question we worked on. So it motivates the question. So the tightness of a space X is at most kappa. If X is in the closure of a set A, then there's a lesser equal kappa size subset, so that X is in the closure of that set. Another way to say that is the closure of the set is the union of the closures of the kappa size subsets. All right, so those are all very well known, very well studied. And then there's a new cardinal variant, newish, I think it was late 80s, by Stavrova and Archangelskis have a paper where they study, might even be called, I don't remember, variations on tightness. And one of the variations was this one. So K stands for compact, and star stands for different than the other variations. So the kappa star tightness, right? So if you're in the closure of a set, then you can find no more than kappa many compact subsets of that set. And you're in the closure of the union of those compact subsets. So I'll just say it again. So if X is in the closure of A, then you can find the most kappa many compact subsets of A, and X is in the closure of the union of those compact sets. So of course, if you have tightness at most kappa, you have tightness TK star at most kappa, because then those can just be singletons. All right, so they introduced this notion, among others, and they studied it, and I was glad to see that I used the same notation for the family of compact sets as Paul did, so okay, thanks. So they studied this, and actually I came on this question, if I remember correctly. Gary wrote to me once and said, have you looked at this question? It's a great question. I also thought this during Paul's talk that I was going to say that sigma compactness is really hard to understand, I've come to understand. So X has sigma compact tightness, so if you put kappa equal L of 0 there, so that's just what we would call it, right? Sigma compact tightness if that cardinal invariant is L of 0. So it's easier to say then, right? So if you're in the closure of a set, then that set has a sigma compact subset, and you're in the closure of that sigma compact subset. And so, as I said, they introduced it in that paper, and our main result about this cardinal invariant was that if X is compact, then tightness coincides with this sigma compact tightness, right? Not just for counter case, but in all cases. But it's still a great question. If you drop compactness, let's stick in the regular spaces or certain Hausdorff, but I prefer Tikhonov, but it's completely open, right? So if you drop the assumption that X is compact, does countable pk of X imply countable tightness? So we don't know. Great open question. And as far as I understand it, Istvan and Jan van Mill were thinking about this question when Jan was visiting Istvan in Budapest. And then Jan formulated another question while they were thinking about it. And then when Istvan and I were driving home from Gary's conference in October, Istvan visited me. He brought up this question. So that's how we started working on the question I'm going to now tell you about. And it's Van Mill's question. Okay, so we went, Van Mill formulated basically a dense set variation of TK star. So let's get some of those definitions. So this is a older, but not very well known cardinal invariant. I think Juhasz gave it its name, delta of X. So delta of X is the density of dense subsets, right? So you take an arbitrary dense subset of X, then the density of that set is no more than delta of X. So delta of X is the supremum of the dense subsets of X. And so we can formulate d sub k, right? So d sub k has nothing to do with delta. But you could say that, so instead of tightness, right, tk, let's say dk, density. So the kappa density, the compact density of X would be at most kappa if you can find kappa many compact subsets whose union is dense. Very simple idea. So a sigma compact space would have dk equal to 0. So of course, d sub k, you can see density, right? Because if it took a compact space, its d sub k would be 1, but its density would be whatever. So anyway, this just gives us an opportunity to define this. So this is our dense set variation of T sub k. So delta sub k star is the supremum of the kappa densities of dense subsets, right? So you take an arbitrary dense subset of X and you ask how many compact subsets of that do you need so that the union is dense in the space, not just in it. Of course, the kappa many compact subsets of Y will be dense in Y will be dense in X. So, all right, so the one that would be most interesting is countable dk delta k star, and so let's call that densely k separable. K for compact. So densely k separable. That's the name we came up with. We were actually calling it Van Mill spaces, but I said the I didn't have a good name for a paper, so we call them densely k separable now. So densely k separable means every dense subset has a sigma compact dense subset. That's what densely k separable means. Every dense subset has a sigma compact dense subset. And what Van Mill asked, no, that's not there yet. So here's just a couple of trivial cardinal invariance comparisons. So the cellularity is below this cardinal invariant, and that's rather easy to see. Because you take a family of pairwise disjoint open sets, compact subsets of that union, every compact set would be covered by finitely many of those guys, so of course you need as many compact sets as you have pairwise disjoint open sets to become dense. Clearly, dk star is less equal to delta, because if every dense set has a dense subset that of whatever cardinality, it's the union of singletons, and so this is trivially less than equal to that. And this is less than equal to pi of x, because if you have a dense subset of x, then the pi weight of that dense subset is inherited, so it has the same pi weight, and density is bounded above by pi weight. So those are some easy comparisons of the cardinal invariance. And very difficult proof, originally not originally, but due to Shapirovsky for regular cardinals. So pi weight of x is a regular cardinal. then that, for a compact space, that equals the delta of x. And then we also shall prove that for all pi weights, the delta of x is equal to the pi weight, right? We're going to need this result. Okay, so I think we've got our definitions under our belt. A couple of examples that are just trivial, just to maybe illustrate something. 2 to the omega 1, the Tikhonov product has countable density, but the delta sub k star is uncountable because of the sigma product, right? So the sigma product won't contain very many big compact sets. So that just shows that the density can be less than this delta. You take a countable dense subset of 2 to the c. A countable dense subset of 2 to the c will have pi weight c. And of course it has countable dk star, and it's countable. So of course the pi weight can exceed this delta k star. And as I said, so the Van Mill question, this is the one we started working on the drive back between Atlanta and Charlotte. So are all compact density k separables, are they separable? So we've added compact. Are all compact density k separable spaces separable? And so the answer, I'll tell you the answer. The answer is yes. Not only are they separable, they have countable pi weight, right? So much stronger. So for compact spaces, density k separable is equivalent to having countable pi weight. So that's a simple to understand statement. The proof, I hope, is a little bit interesting. But I would just add that just like with tk star, we know nothing if you drop compactness, and that's true here too. I've been working on it, and I literally know nothing. So does delta k star equal delta of x? So in other words, does the kappa density help you? Not at all, right? So if you take an arbitrary Tikhonov space, you take it, can you find a dense subset so that it takes you as many compact subsets to get dense in that as points? That's really. So in other words, what you're really trying to do. I have a question right at the end of the talk. How about this? Does every Tikhonov space have a dense subset with no uncountable compact subsets? I don't know. So take a Tikhonov space, find a dense subset. Can you find a dense subset that has no uncountable compact subsets? I don't know the answer to that. Since that was at the end of my talk, I guess. All right, so I'm going to go sketch the proof. Pretty much more than a sketch, but let's see. Oh, I forgot to mention that the tk star thing, I worked on that question with Justin Moore. We were at this summer topology conference several years ago when it was in Minnesota, and we started talking about it, and we ended up having some progress, but not a lot, so really worth mentioning. But we had some ideas in that paper, and that's what got Ishvan interested in that paper, I think. So one of those ideas was the relevance of left separated, okay? So a sequence in a space is left separated. You have to explain to me how to remember left versus right separated. Left separated, that way is open. So points are not in the closures of the initial segments. So that's what left separated means. And there's an old result of Ishvan and Topology that a compact subset of a left-separated space is scattered. Not too difficult to prove. I didn't look at their proof. I thought it was proof. But it's not trivial. But anyway, it's true. I'm not going to sketch that proof. So a compact subset of a left-separated space is scattered. So we're on our way to figuring out how to get few compact sets, right? So by getting left-separated, we can shrink the number of compact sets that are available. And it's also true that a compact first countable scattered space is countable. So that might be well known. I don't know if it's well published. I don't know. So compact first countable scattered spaces are countable. That'll be another tool in our proof. So compact subsets of a space, right? And if that subset is both G delta separated, so what I'm going to mean by G delta separated is you can find cover, you can cover by pairwise disjoint. No, they don't get pairwise disjoint. They just, each point is in a G delta set that hits the set in exactly that point, right? So sort of like a generalization of discrete. I guess we can discrete in the G delta topology. So if the space is G delta separated and left separated, as in this sense, then putting these two things together, you can see that compact subsets are common. Well, if you take a compact subset of a left separated space, it's scattered, and it's in relative topology, it's first common, and so therefore it's common. So this is going to be our main tool, but we've got to do some stuff in order to make this tool useful. All right, so the first thing was a weight reduction. So it turns out we can get a weight reduction. So a definition of a quasi-open map, it's not my definition. So a map is quasi-open if images of open sets have a dense interior. And that's equivalent to the pre-images of dense sets are dense. So it's just, you can take that as a definition. Pre-image of a dense set is dense. All right. So if you have our space X is our counterexample to having small dk star, but big pi weight. And if you can find a quasi-open continuous image, so f of x is a quasi-open continuous image, then in this kappa density, K compact density is smaller than this one. Why? And I should be assuming that, no, I don't think I need, no, I don't have to assume anything. Take a dense subset of f of x, pull it back, it's a dense subset of x. Being a dense subset of x, it has a family of compact subsets whose union is dense. Send those forward, that's a family of compact subsets, and the image of a dense set is dense. So okay. So that's useful. So the quasi-open continuous image will shrink the compact density. And now you can prove this. Literally, you can prove this because I'm not going to. If x satisfies that, so this is like a counterexample, right? So the dk delta k star of x, it's not easy to say, right? So the compact density is kappa less than the pi weight. Then, using elementary submodels, this is my proof. Take an elementary submodel, closed under kappa sequences of size 2 to the kappa. That gives you you can let me start again. And I should have said x is compact. That's very important, and I forgot to say it. X is compact. You throw it into a Tikhonov cube, you get a big set of coordinates of size 2 to the kappa. And you project the x into that set of coordinates. Now the weight is at most 2 to the kappa, so of course the pi weight is at most 2 to the kappa. And it turns out, because of the elementarity and the remember that this is this bounds the cellularity. So it's because of the cellularity. So the cellularity is at most kappa, and that allows you to prove that the map is quasi-continuous, quasi-open. So that projection map is quasi-open on x, and so therefore the delta went down, so the image of x has delta no bigger than x had. And again, because of elementarity, you can prove that y can't have the pi weight of y can't go down below kappa. The elementary submodel can't have a pi base of size kappa, otherwise elementarity would tell you that x had a pi base of size kappa. So we get a quasi-continuous image with pi weight exceeding delta, but pi weight no larger than 2 to the kappa. Right? So if there's a counterexample, there's a small one. So in the countable case, if we're just looking at the countable case, we're looking at compact CCC because the delta sub k was bigger than equal to cellularity. So we're asking, is there a compact CCC space and the pi weight bigger than equal to c, less than equal to c, because of this lemma, that is a counterexample. So we can assume the pi weight is at most c and that it's compact CCC. All right, well here's the main tool. Each compact crowded, no isolated points. CCC space can be partitioned into compact G deltas. such that every non-empty set meets C, many members of the partition. So there's a partition by compact G deltas. Every non-empty open set meets C of them. This has nothing to do with density. This might be an independent interest. Maybe it's no, I don't know. Throw X into a taken off cube of the appropriate suffix. Take many people don't like this, but that's the way I work. Take a continuous increasing chain of elementary submodels, countable elementary submodels, and have the first one contain X. We're just using these elementary submodels to grab big pieces of the index set. Okay, so big, they're countable, but they're smart countable. Right? So M0 grabs a smart countable subset of the index set. So we're going to look at G deltas of this form. You just take, that's a countable subset of the index set. Take an arbitrary function from that countable set into the interval. And I'll use this notation. Many people do. Right? This stands for all functions in the full product that extend that countable function. Right? So you have this countable partial function, and bracket T stands for all functions that restricted on those coordinates equals that. So this is the G delta, and I'm only interested in the ones that hit X, and I just call that the subscript X, meaning the part that hits X. So that's simply a definition, and you might think in terms of, this is my attempt at a partition. This is a partition of X. Like just let T range through all those ones and look at all of them. And what it is that that's the projection of X into this Hilbert cube. And so that would work, except those things, some of those things might have interior. And that wouldn't work because I can't have any of those guys having interior, because I want every open set to hit it in full size. If none of them had interior, we'd be done. That would be your partition, because every open set will project to an uncountable image, but it would be a compact, uncountable subset of the Hilbert cube for the cardinality C. So that would work. I'm probably out of time.
Go ahead.
Okay.
A couple minutes.
All right. So I probably don't have time to go over this very carefully, but so maybe bad news. Okay, this isn't an ST set, but it's at most countable. Why is it at most countable? Because those interiors are pairwise disjoint. The space is CCC, so this is at most countable many of them. So the bad news is that we might have a Suslin tree. So if you said there's no Suslin trees, this won't happen. But it's also true that and why is it a Suslin tree? Well, that's because it's CCC. So the levels that are most countable, we also can have a uncountable descending chain because of CCC. And so that is, as I said, a Suslin tree. And all you take is minimal elements of minimal elements of the family of all T alphas. So as soon as they become lower dense, you take that in your partition. So you've got this tree of all such, ranging over all alphas, all such guys. If you follow a member of X, follow it down, eventually it becomes lower dense because this has no uncountable chains. And there's this minimal place that it becomes lower dense, that you throw that in the partition. And there's an argument to be made, why is it true that the image of every open set, it's seen many of them, but don't have time. All right, and so I can finish by saying, okay, here's the final result then. If X is compact, crowded CCC, and pi rate at most C, then there's a dense set Y such that the density, the kappa density, the compact density is the pi rate, and so if you're K separable, then you have countable pi rate. That's the proof, and I'll just go a little quickly. So Juhasz and Shala set us up, ready to roll. They said, well, X has pi rate, whatever. There's a dense subset of X with that density, right? So there's a dense subset of X with that density. I examined their proof very carefully, looking how to modify it to be useful in this context, and it turns out it was trivial. All I got to do is take the Aleph zero closure of that dense set. So let Y be the Aleph zero closure, right? So every countable subset of Y0, take its closure and throw it in, and you didn't shrink the density, right? So the density of y is no smaller than the density of y0, because everybody in y is in the closure of a canonical subset of y0. So we still have big density. So this density is equal to the pi weight, and the advantage of this y is that these G delta dense. Okay, well, we have the partition from before, and it's like a diagonalization argument. Now this is a partition. Every open set gets C many members of this partition. There's only C many open sets to worry about. We'll go along and we'll inductively pick a left separated. By recursion, we'll define a left separated dense subset. So there's some argument to be made there, but you can find a left separated dense subset. We can look at the alpha member of the pi base, and if it didn't hit this set already, then the union of the zero sets that we've already chosen can't cover it because we hit C many. So get a new one, and off you go. And that does it. I won't even go to the next slide. That does it because we've got our left separated. The family we've chosen, inductively chosen, is left separated and dense. And it's G delta partition, right? At every point in that left separated set has a G delta set that hits this family in singleton. And so by the argument 2 slides ago, that guy, compact subsets are countable. And so that's it. And so there's the question I mentioned. Just while I was thinking about this stuff, trying to draw unpack this, maybe there's an easy example here, but
Any questions? Okay, let's thank the speaker once again. Next talk in about 2 minutes. Our next speaker is Tim Fong, who will tell us about spaces with a Q diagonal.
Thank you, Kevin. So this line of research is following KP Hart and Allendon's result about spaces with a p-diagonal, with a irrational diagonal. So Q here is the set of rationals. So basically, we try to prove some materialization results based on the property of the space X squared minus diagonal. So let me try to define what's Q diagonal first. And in case you miss Paul's talk this morning, I'll start from the beginning. So it's a definition, directly set, and so a partial order with some properties, and a directive set is a partial order set such that any two elements you have an upper bound. And some examples, and the examples we are interested in this talk. For example, omega, the set of natural numbers plus 0, and omega to omega, which is also isomorphic to the irrationals. And, the general one here, which is a collection of compact subset of a separable metric space, for example, KR and KP and KQ. So I like to use the set of real numbers, irrationals, and the set of rationals. So some properties will about this directive set. First is complementarity, which is a minimal size of a confinable subset of a directive set. And some examples, and we know that the confinality of KR is RF0, and just take negative n to n with closed intervals. And omega to omega is D, and the confinality of KQ is also D. And additivity is the minimal size of the unbounded subset of the directive set. For example, we have the additivity of KR and omega to R and KQ. So real numbers, irrationals, and rationals. And caliber, so that's another nice property about directive set. So directive set has caliber kappa, lambda, gamma if we have for any couple size subset, there is a lambda size subset S1 here. For any gamma size subset of S1 is bounded. And what we are interested is just for any separable metric space, it has caliber omega 1 to omega 1 omega, which means every uncountable subset of Km, we can find a countable subset of which is bounded above. So that's all we need actually. And so how do we compare two directive sets? So just 2Q ordering. So we will say that Q is greater or equal to P. If we can get, if we can have a mapping map all the confined set of P to Q, right, that's the property of this mapping here. So if you have a dead-inclined complete, which means every bounded subset has at least upper bound, we have the equivalent definition here is there is an order preserving mapping such that this map P to a confined subset of Q. As some examples, KQ is 2P equivalent to omega, and KP is 2P equivalent to omega, and also we have that in the sense of 2P ordering, KQ is the biggest. And so some applications, so if you have a second countable space, this is completely materializable if we have this issue, and also we have this, if you have actually compact, then if you have omega to omega is 2P greater than the collection of compact subset of the off diagonal space of X, then X is materializable. So that's some using the term of 2P ordering, we have this two classical results. And so here let's see the definition of M diagonal. M here is a separable metric space. We say that a space is strongly dominated by M if you have, not strongly, so don't worry about strongly, just dominated by M if you have a Km directed compact cover. So we don't want to consider the confinality, just the compact cover that may not be confinable. So this collection is Km directed if we have we can get KL is a subset of KL prime given L in a subset of L prime. So that's directed. And so M diagonal, M in a separable metric space means X squared minus the diagonal is dominated by M. So which means we can get a Km directed compact cover of this off diagonal space. So that's the definition. So KQ Q diagonal means we can get a PQ directed compact cover of X squared minus delta. So let's see the starting point of this line of research. And this is starting from the any compact space with the G delta diagonal is contractible. So if you have X is compact, G delta diagonal is equivalent to have an R diagonal because you have compact space. Every closed-up set will be compact. And there's a problem raised by with mathematicians, and they are asking if you have an R diagonal as contractible, what about irrationals or rationals or any separable metric space? And okay, so first where Tukey ordering is used. So basically, if we apply Tukey ordering, if you have Km is greater or equal to Km, so any space has a N diagonal will have an M diagonal. So basically, we are looking for the upper bound of Km such that M diagonal implies contractible. So everything less will be good. So that's where the Tukey ordering where we use it. And some recent results, and in the same paper, they proved any space with a P, which means irrational, is contractible under the assumption modeling action omega 1. And under CH and Allen and Sanchez proved any compact space with a P irrational diagonal is contractible, and with KP Hart, they extended the result to a ZFC result. And so now let's see why KQ is different. Let's see what's the difference between KQ and KP. Framley and Spee proved after omega you have the unique sector, which is omega 1 omega. And Paul and Anna, they proved KQ is between omega 1 to omega times omega 1 and omega 1 to omega times alpha 1 to the less than omega. And they also proved after the K irrational seems getting crazy, so there are 2 to C size anti-chain after the irrational. So KQ is one after the irrational, things are very complicated. And so now let's see this. Let's see how do we compute from here. So basically, techniques, if you have Tx is omega, X is compact, and it's not hard to prove X must be contractible. Just use a tightness is omega. So basically, the idea is try to prove the tightness of X cannot be uncountable. So basically, we try to construct a contradiction when when the tightness is greater than omega. So that's the approach. If you have a contradiction, then that's the only case actually. And so there's a result given by Sanchez and Kirchhoff, and they proved if you have omega bounded, which means every countable subset closure is compact, non-compact space. If you have a Km directed closed subset, then this X contains a compact separable subspace which maps continuously onto I omega 1, but we don't need I interval here. We just need the discrete subset 0, 1. So this 2 here is a set contains 0, 1 just with a discrete topology. So what we want to do next is let me see. So let's try. So what we want to do next is we try to investigate what happens in 2 to omega 1. Try to get a contradiction from 2 to omega 1. So a big set was introduced by Allen and Sanchez, and this right. And so if you have Y here is big, which means after some kappa, you have a projection on 2 to omega, you get everything. So after kappa. And so that's very big. And so they proved if you have a KP directed compact cover of 2 to omega 1, then 1 this is big. And now if we have T tightness axis is uncountable, we can construct we can get a free sequence of length omega 1. Now from here we can get a compact subset which has a p diagonal. But if you have this assumption here is true, this will be true. Then if you have X map continuous onto 2 to omega 1, then X cannot have a p diagonal. So basically, that's where the contradiction is. It's just you get from the big space, you get a compact subspace which has a p diagonal, but this subspace is mapped continuously onto 2 to omega 1. So by the second line here, you have a contradiction. So that's where the idea works. And so what I did here is just first, this is a very quite natural property. If you have a decreasing sequence of big set, intersection must be big. And I extended I extended this assumption to if you have a P here directed set, P has caliber omega 1 omega. Remember the P and B separate metric space. Then what? Then KP has omega 1 omega. So Km has caliber omega 1 omega 1. Then if this is true, then the same result holds. So what's next is how do we construct our prediction? We want to get for what kind of separable metric space this condition holds. So this is an assumption. This is proved, but this is an assumption in my result. So what I want to do next is figure out for what kind of directed set. If you write 2 to omega, if you get a P directed compact cover of 2 to omega 1, then one of this set is big. So I want to identify what kind of P this condition is here holds. Then that's natural, same contradiction we have. So instead of investigating the big set, we need to do some tiny set. I look at T here tiny. WT means a little bit bigger, so weaker T. So T is a tiny set. WT is a little bigger, and T here means for a set A here is tiny. If you for any subset to less than omega 1, you can extend it putting finite pairs such that the set I mean, all the, how do I say that? All the function from omega 1 to 2, which contains p prime, intersect is empty. So you miss a big open set for every finite, every countable subset of 2 to less omega 1. So you can extend it, that open set will never intersect A here. So that means our set A here is very, very tiny. And for a little bit bigger set WT means you can extend it for countable many times. Right, and so that's the definition of T and WT. And so we can show that countable union of T has property WT, and we can show that this condition here holds. And so, right, if you have a cluster point in here, then this one has property non-T. So, and quite natural to ask this question here, can 2 to omega 1 under the G delta topology? So G delta topology means every open set in 2 to omega 1 is a countable intersection open set of 2 to omega 1 in the Tikhonov product, G delta topology. So can 2 to omega 1 be represented as a countable union C size, because the density of 2 to omega 1 in the G delta topology is 2 to omega 0. So is a collect like lower dense subset. For sure, if we don't consider order here, and under Martin's axiom omega 1, 2 to omega 1 here is C, so you take all the singletons and take a unit, for sure you get the whole set. So this is impossible if we don't consider order here. And okay, now we want to consider order. So under the assumption B is greater than omega 1. Okay, so we can show that if you have an omega to omega directed collection of subset of 2 to omega 1, if you have this assumption here is true, and this condition holds, and the union is WT, it's not even close to the 2 to omega 1. It's just a little bit bigger than tiny set, and has property compact plus not big implies T. So that's where the connection is made. And so if we assume 2B is greater than omega 1, we can show that this has this property T here. So which means if you combine these two results together, if you assume B is greater than omega 1 and KF here is brings is actually more is omega to omega times Aleph 1 to, this is the upper bound of KQ, so that's where we use the 2Q order. Directly compact power 2 to omega 1, then we can get 1 with KF must be big. So that's what we can get under the assumption B greater than omega 1. And what about the other cases? If you have B here is greater than B, which is equal to omega 1, we use use this result, and the proof here is very, very, very similar to Alan and KP's proof. You just push it harder using the Hausdorff metric on KF. It's very, very similar. Just push it a little bit harder, and we can show that if you have a Km directed compact cover of 2 to omega 1, then for one of this element, Kf is big. And so that's my last slides. So now from our discussion before, we have a summary here. So for KQ, we discussed D equal to omega 1, D greater than B, when B is equal to omega 1 and B is greater than omega 1. So all the possible situations, all the possible assumptions we have, well, K must be big. So which means we have our prediction. So any compact space with a Q diagonal is retrievable. And because we show that the contradiction holds, no matter what separable metric space we use under this assumption, so we can see that any compact space with an M diagonal for under this assumption is not hold. So any compact space with an M diagonal for some separable metric space is retrievable. So now the problem left is what happens in under other assumptions, either E equal to omega 1 or B greater than omega 1. So I don't know the answer to that, to what happens under that two assumptions. Any suggestion or any comments will be appreciated. Thank you very much.
Are there any questions?
What happens in countably compact spaces?
We can show that any pseudo-compact space with Q diagonal is cosmic. Right, let's use a proof given by Kachu and just naturally extend any pseudo-compact with a Q or. So if you can show this is true for compact, their proof works for pseudo-compact, being cosmic range.
Any other questions? Okay, let's thank the speaker again. The next talk will be in about 8 minutes.
sets part from my talk here. Now, is there anyone here who has not heard me lecture before? Oh, okay, and some young ones too, so.
Do you have to listen? Do you have to listen?
What? And furthermore, I think you probably remember, anyway, I am an incredibly old man and have, for most of that time, been able to avoid working for a living. If you think that sounds good, then I have some advice for you, which has done wonders for me. And that is to find somebody who is smarter than you are and get them to put your name on their papers. Primary among those people is Donald Strauss. Now, I actually committed retirement at the end of the last academic year. And so over my 50 years of teaching, I had exactly one sabbatical. And it was the spring semester of 1990. Now at Howard, the spring starts in January. But in any case, I would like to claim that that's probably, in terms of publications, one of the most productive sabbaticals ever. So I want to tell you about it briefly. What I did is did some travel. So the first thing I did was I visited John Bergman for a week down in Richmond, and it resulted in one publication. Then I went home a little time and visited Vitaly Bergelson for a week in Columbus, and that resulted in 2 publications. I went home again and visited Jan van Mil in Amsterdam for a week, and that resulted in 1 publication. Now, I didn't go home from there. I went directly to Sheffield and visited John Baker and John Kim for a week, and that resulted in 2 publications. And while there, John Kim introduced me to Donald Strauss, which has resulted in 71 publications. I figured. That's not all right, now, all right, what I'm talking about today is beta S. S is a discrete semigroup. And a bit of the algebraic structure of beta S. Okay, the operation on S extends to S, to beta S. So that beta S is a compact, of course, also, of course, right topological semigroup, Now, right topological, that means that if you take most of P of Q is Q times P, then that function is continuous. So multiplication on the right is continuous. Now, some people call that left topological. And I would say, why on earth would you call it left topological if multiplication on the right is continuous? And they say, why would you call it right topological if it's continuous in the left variable? And it's actually worse than that, because of course you can do it this way or you can do it the other way. And I used to do it the other way, and so you can have it be this one continuous, and you can call it right or left, or you can have the other one be continuous and call it right or left, and all 4 occur in the literature. So you have to check. And the other thing is that if S is in S, then lambda sub S is continuous, where that's multiplication on the left. Okay, so as a compact right topological semigroup, it has a lot of interesting algebraic structures. It has K of beta S is the smallest ideal, smallest 2-sided ideal. And that is the union of the set of all L, such that L is a minimal left ideal. And it's also the union of the set of all R, such that R is a minimal right ideal. And if you take a minimal left ideal and intersect it with a minimal right ideal, that's a group. All the left ideals are isomorphic, all the right ideals, minimal left ideals are isomorphic, all the minimal right ideals are isomorphic. These groups are all isomorphic. If you have two minimal left ideals, then L intersect R and L prime intersect R are algebraically and topologically isomorphic. So in other words, there's one function, namely multiplication on the right by the identity of the target group, that makes them both, that is both an isomorphism and a homeomorphism. Okay, that's part of the structure here. Now, whoops. The following is almost true.
That's alternative true.
No, actually, well, there is another word for almost true, of course. Yeah, false. But, okay, the statement is that if X is an algebraically interesting subset, S, then either X is compact or X is not bereft. Now, well, Donna points out there's an easy counterexample which makes that certainly false, because N is the algebraic center. That's certainly an interesting algebraic object of beta n under addition and beta n under multiplication, and it's not compact and it is countable, so it's bereft. However, let's change the root of the Stonechek remainder. We have no counterexamples to that statement. Okay. Now, what I want to tell you about here is some particular places. Let me see if I'm not skipping anything. Okay. For the moment at least, let's assume that S is cancelative. For what I'm going to talk about right now. Now, incidentally, the abstract and the version of this paper posted on my website are incorrect. It says right cancellative and weakly left cancellative. Now, weakly left cancellative says that if you take A and B are fixed and you take the set of all S such that AS equals B, that's always finite. So that's weakly left cancellative. That's called a left solution set. Of course, you see, if it's left cancellative, it's supposed to singleton. Okay. I don't know whether what's stated in the abstract is wrong. We don't have a counterexample to it, but the proof doesn't work as written. But it does work if you take cancellative, and if I had time, which I might, I can tell you some weaker things than cancellative that make it work. So that's an interesting point there. But let's look at that then. And the smallest ideal is an interesting object, which is a subset of the Stonechek remainder. Okay. I should point out, of course, the minimal left ideal if P is any element of there, the minimal left ideal is that continuous energy compact space, so they're compact. Okay? And the closure of the smallest ideal is again an ideal, so it's an interesting object, and it's compact. Okay, but let's look at these other things. The smallest ideal of beta S, the set of products, the idempotence, okay, and R, can anybody see that thing that far? R times S star, okay, where R is non-principal. Okay. All of these objects, and notice in particular that includes the minimal right ideals. Because if R is in a minimal right ideal, then R times S star is that minimal right ideal. So all of these objects are not Borel under this circumstance. And now, so how does the proof go? Well, there's basically three parts. A, if B is the set of Borel sets, then they are contained in the set of all subsets of, well, of beta S, but in particular of S star. Well, let me put beta S here. Such that A is the union of, at most, C compact sets. Okay, that's pretty easy because remember, did I say that? I didn't say that. S is countable. Okay, for what I'm talking about here. I don't know the answer if S is not countable, so that's another issue. But it was, S is countable, so S has C subsets, and the closures of those form a basis for the open sets, and they're all compact. And so the open sets and the closed sets are contained in there, and then you just show that it's closed under cantilever unions, and you're done. Okay, so that's an important thing, and that's simple. B, we construct a function phi taking S to N, and it has the property that if you take phi tilde, taking the continuous extension, taking beta S to beta N, that phi, if C is compact, then phi of C is finite. Okay? So, looking back on here, that says that if you have a Borel set, erase. So if B is Borel, then being the union of most C compact sets with the size of the image of B is at most C. Now that, constructing that phi requires, again, the proof on that requires that S is weakly left canceling. So that's a part of what's done there. And then finally, on each of E of beta S, S star, K of beta S, and R times S star, until that assumes 2 to the C values. Almost the best, I mean, what is required for that last part is that if P is not equal to Q in S star, then the set of all S in S such that SP equals Q is finite. And the mistake that we had was thinking that that followed from being right cancellative. Okay. It almost does. Almost again. As long as one of these S's is left cancellative, then that does work. But anyway, so that's what's required, and it certainly follows from cancellativity. Now, let me point out, and incidentally, notice we did have a little topology in this talk. Okay. Anyway, I'm leaving that again. So note that neither right nor left cancellative is good enough, because suppose S is right 0. That means that S times T is T, for all S and T. Okay. Well, then beta S is right 0. And if you get bored in the subsequent talk, then you can verify that. The simple continuity does it quite well. Well, since beta S is right 0, then K of beta S equals E of beta S equals, okay, and that is equal to beta S, and S star is S star, and R times S star is S star, and so, well, see, we still don't have a counterexample. Those are all Borel because they're all compact. Well, what about left 0? Well, K of beta S is E of beta, everything's an item. E of beta S equals beta S, S star times S star. The only difference down here is that goes to singleton R. Still compact, but again, the proofs don't work. Now, I mentioned that what one does for part of the proof, one requires weakly left cancellative. So what about, suppose you had weakly left and weakly right. So every left solution set is finite, every right solution set is finite. I'll take n under maximum. The maximum, the value is the maximum. Then P sub Q is Q if Q is in N star, and P if P is in N star and Q is in N, and of course if they're both in N, it's simply the larger of the two of them. So if you look at that, that means that N star is right 0 again. So K of beta N is N star. E of beta N is everything. Everything's in idempotent. N star sup N star is N star, and R sup N star is equal to, actually, yeah, that's right, it's right 0, so it's going to be N star. Okay, so again, you have, so that the results about not being Borel don't work under weakly left and weakly right. They don't work under left cancelable. They don't work under right cancelable. And what they do work on, let's take note on this quickly. If you have a finite set of elements of S which are not left cancelable, and a finite bound on the sides of right solution sets,
Next talking about 4 minutes. talk by Jared Holzhauer, who will speak on calibrating the size of complicated closure.
All right, so the inspiration at the very beginning of this talk was just this picture that I hastily took with my phone last night after I realized I wanted some pictures, which is if you have this Borel equivalence relation on reals, what I should have said there, there's a lovely little picture here of, okay, perhaps on a single point, 2 points, all the way up to count the many points. The only thing that can happen after that if the equivalence relation is Borel is that its size continuum, Cantor space, embeds into it continuously. And then, weirdly enough, the only thing that can happen after that is R mod Q, very, very bizarre quotient space, embeds into it. And then the big weird opening after that is just chaos with weird portions of order in its entire field of study. So, big cloud means that people have spent decades searching for this stuff there. All right, so that's what we have. This comes from these classic theorems of invariant descriptive set theory, from Silver and Harrington and Laveau. So you have a co-analytic equivalence relation. To refresh people who might not be as familiar with that, analytic sets are projections of closed sets. Co-analytic are complements of those. Okay, so just a little bit more complicated than Borel. Then either the quotient is countable, or you have a map on the level of the reals itself, which takes inequivalent things to, so unequal things to E inequivalent things, which then creates this embedding from R into the quotient space. Here in Topology, Laveau backs off of co-analytic, bumping down to Borel, and gets you this farther bit that either your quotient embeds back into R, or this weird quotient space embeds into you, basically. And part of what's going on here is you're kind of thinking in terms of definable structure. Okay, so R is linearly orderable in a definable way. You know, we know this. R mod Q has problems with linear orders. If you linearly order R mod Q, you construct a Topology set. Okay, so those have to be very strange orders indeed. Definitely not Borel. All right, and the proof doesn't actually use Borel sets in particular. It uses some strange thing from descriptive set theory called sigma 1-1. Okay, so to describe that, we have to go into what descriptive set theorists actually do, which is not look at the reals, but look at the irrationals. So that theorem back on that page here, continuous is maybe a bit of a lie. Bare class 3, right, is maybe literally what's happening. Or if I want to be more specific, I could say, you know, replace R with the irrationals. All right. So descriptive set theorists don't care about those differences because we care about things at the Borel level, not at the continuous level. All right, so you replace R with omega to the omega because it's got a very lovely combinatorial structure. Closed sets are formed from, of the products are formed from just these branches of trees on omega to the n. So here's this picture here. Your tree consists of partial functions from omega to omega. Those are the nodes. And then branches are just, you know, full functions, right? So the tree controls what reals show up by controlling what their initial segments can be. Okay? So T is the tree, bracket T is the body of the tree or the branches. And then you can take projections of the body. So you're looking for reals that can be paired with other reals so that all of their initial segments show up in this 2D tree that you have now. Okay, so sigma 1-1 is, well, sorry, I back up. All closed sets are just bodies of trees. That's a beautiful thing for DST. Analytic sets are projections of those trees. And sigma 1-1, light phase sigma 1-1 as we call it, requires those trees to be computable. Okay, so an initial segment being in there has to be a computable relation. So in particular, sigma 1-1 is a countable collection of subsets of the reals. Okay? So the original proof uses this to either form a basis for topology on the reals, called the Gaine-Harrington topology, or as a coset to force with. Okay? All right. But thinking in terms of those trees leads to this kind of natural extension. Okay? Why settle for choosing naturals? Why not choose ordinals below some kappa? Okay? So throw in as your final piece there a kappa, But so as to still create sets of reals, make it so it's only coming into play with the projection bit. So now you've got these reals, and you're looking for a function from omega to kappa, so that all of the initial segments cut off uniformly show up in this tree that is now containing partial functions from omega to the n cross kappa into 2. Okay. So that's it. This is it in notation. Projection of the tree is all those reals so that you can find a function so that we uniformly cut them all off to get the partial functions. They show up in your tree that's controlling it. What this does philosophically is allow you to kind of incorporate these long rankings of your set. Okay? If you try to do this with Brel things, you can kind of uncountably rank your set of reals. If you allow larger kappas, you produce things that are not Brel. Okay? Co-Kappa-Suslin means its complement is Kappa-Suslin. Analytic is the same as Omega-Suslin, that was basically on the previous side. Okay? This gets kind of dumb under the axiom of choice if you allow kappa to get too big. So if you make it continuum size, you can just code the reals into that branch that you want to put in. So it's only a form of definability when you make it kappa below the continuum. Okay, so being omega-Suslin, right, is a form of definability slightly above Borel. If you have space between omega and the continuum, you have space to have higher degrees of definability. That's how this works. All right, so there's this lovely, I think, very overlooked, maybe, theorem of Harrington and Shalot from 1980 that extends Silver's theorem. If you have a co-Kappa-Suslin equivalence relation, and as Shalot states it, E is still an equivalence relation in the next world, then either R mod E is no longer countable, but it embeds into kappa. So it's well orderable of size controlled by its complexity, or R embeds into the quotient space. Cantor space embeds into quotient space, really. The tools here are weird. This is a weird paper. It uses infinitary logic and inner models to sort of bound collections of statements from infinitary logic to run something similar, sort of, to the original Silver's proof. Okay, but some notes here. This next world business, this still an equivalence relation after Cohen forcing, right? That didn't show up in Silver's theorem because of Schoenfield absoluteness, which tells you all of those statements asserting that your Cohen equivalence relation was an equivalence relation are low enough complexity that they're absolutely modeled as EFC. Bumping up the complexity of the equivalence relation allows for the possibility for that to break after adding reals. Okay. A natural way to ensure that it doesn't break is to shove your equivalence relation inside of some universe of determinacy. This is not to assert that determinacy is somehow true. What we're using is the fact that universes of the axial choice of large cardinals have interior universes of determinacy, and that pretty much the only way to get interesting Susan sets comes from inside models of determinacy in the first place. So if they're already living there, and that's what you need to get Harrington and Shalot to work, just work there in the first place, and even gain some control about where your embeddings are coming from, right? So that's the philosophy. So this is a restatement of Harrington and Shalot. If it's a co-Kappa-Suslin equivalence relation and it starts off in the universe of determinacy, and in that universe you can embed it into kappa, R embeds into it, and these choices are distinct. Okay? R in particular is not well orderable in that universe. Right? Okay. So that was just a restatement of the same slide. All right, if we're going to play with AD, might as well play fully. This is a result from Casado and Ketcherson in 2011. Right? Just drop the Suslin bit of it, and you get the full trichotomy back with a loss of precision. You no longer need to say showing up in some kappa, you just say it's well orderable, period. Or R embeds into it, and it embeds into the alpha for some alpha, I don't know what it is, but it's some alpha, or R mod Q embeds into it. Basically, it's well orderable, linearly orderable, or not linearly, not definably linearly orderable. Definable should always come before those. But something called treatable. Okay, some partial order structure stuff, basically. Completely different tools in this theorem as well. You use Boolean algebras defined from subsets of the ordinals and reals, and you use Martin measure to stitch all of them together. which is the whole thing about Turing degree, so it's inner models and determinacy. It's kind of all.
What does 2 to the alpha mean here?
It's not the ordinal arithmetic, it's the, yeah, so it's really just a cardinal.
Oh, it's a cardinal.
It's
It's not a taken off product.
It's not, no, yeah, it's just the cardinal. Okay. So,
It's a power set cardinal.
yeah, that's right, it's a cardinal, yeah. So this creates this kind of picture, where you have omega and stuff below it. On one end it goes into the cardinals, on the other end it goes into these powers of cardinals. And this is to indicate that there is madness inside of here. This is very complicated. And you go to R by Q and you get more madness. Okay? So that's kind of what's happening there in determinacy. Now, where am I stepping in? Okay, Harrington law doesn't have the full trichotomy. He just recreated somewhere. Caseto-Kettersid isn't as specific as it could be. Even if you start with these co-Kappa-Slusen sets, right? You don't get that kappa bound because you're running something through this horrible ultra product that loses all kinds of precision. So unless you can somehow dig deep into the ultra product, you're not going to recover that. But also, why are we using so many different proof methods to prove basically the same things? This was sort of bugging me. So I was like, I just want to fill this in, right? Fill this in with what it should be, using techniques that mirror what happened originally, right? So I want a nice point class with point class properties. I want to do a true set theory. That's my dream for this, okay? All right, so we take the infinitary logic and create basically a semantics for it. And we do that through these infinity parallel codes, okay? So you start with a basis, countable basis for your topology. You let the code that starts with a 0 followed by a natural number correspond to the set that is just that basic open set. You start with a 1 followed by a sequence of other codes, that's an intersection, and 2 followed by a code is a column. And call all of these codes be infinite. Okay. All right, if it's a countable length code, you just made a Borel set. Congratulations. Okay? If you allow the code to be uncountable in length, these are ordinal lengths, right? These are well-founded constructions, basically trees telling you what to do. Then you do lose a little bit, because saying that if you code the empty set, or saying that one set codes a subset of another set, are not absolute statements. Okay, those can change from universe of ZFC to universe of ZFC. It's a bit of a problem. Okay, so what do we do? All right, well, first let's just define our point class. So we're going to start with a tree, something maybe witnessing that something is Susan. And we're going to pull out a little inner model theory that I don't really want to get into, but alpha is going to be the least admissible ordinal for this modification of alpha. So this just means it satisfies a good amount of ZFC. In particular, it satisfies something called sigma zero collection, which means you can basically, you start with things in there, you do simple enough operations, they stay in there. Okay? All right. So code C is in our point class. If it's an intersection of codes, infinity Borel codes that live inside this model, and that entire, maybe in some sense, subclass, right, from the perspective of that model, is sigma 1 definable. So you only used existential quantifiers over that model. So gamma is corresponding to this light phase sigma 1 that showed up earlier, and the infinity Borel codes that are in the model correspond to basically Borel. That's the idea. Okay. Okay. So we can treat this kind of like a point class. It's closed under finite unions. It's closed under reasonably encoded intersections. You can extend the Borel codes to product spaces in kind of a natural way, and it's closed under Cartesian products and projections. More importantly, it contains the code for the set that your tree was encoding. Okay, so you recover that like code, or that whatever the tree was corresponding to. All right, so that's nice. Now with this model in mind, we can define a code being consistent. All right, to borrow the terminology from the syntactical infinitary logic. So consistent just means it's non-empty after you push it into a context where that's an absolute statement. So do a collapse forcing. Collapse kappa to omega. Now saying it's non-empty is absolute. So just check it there. Okay. Same with this ordering. Put C less than or equal to D if it's a subset after collapsing. Okay, so everything just gets checked after the collapse. It's a minor irritation. All right. The good news is that for the codes that are contained in my model, those are actually relatively simple statements. All right. Admissible structures are good enough to understand forcing in particular. So definability of forcing and stuff comes into play, and I can talk about this from inside, which is nice. All right. We recover versions of these syntactical things, but in a semantic way. So start with the code in gamma. If it's inconsistent, then it's inconsistent because of an initial segment of its intersection, proper initial segment. So without loss of generality, all of these codes in gamma have like alpha, so just the full size of the structure. And you can cut it off before then and get an intersection which is inconsistent before that. In particular, if it's a descending intersection, so they're all just following down, then just one of them was inconsistent. Right? This is a very actually strange thing when I first thought of this, because like a countable intersection of Borel sets that's empty doesn't mean that any one of those Borel sets was empty, right? But omega isn't admissible. To go admissible, you have to go to something called omega 1ck, right? The first countable ordinal which isn't computably mapped onto by omega. Okay? And so if it's a long enough intersection of Borel sets, then this compactness criteria happens, and if that long intersection is empty, then something leading up to it is empty. It's very weird. Unintuitive in my opinion. All right, and then this is bar-wise completeness. Fixing something in gamma and looking at everything bigger than it is a relatively simple statement. So these are some of the tools you can use with this point class. Okay. So we were able to produce a semantic proof of Harrington-Shalom that mirrors the original proof of Silver's theorem, if you're familiar with it. Start with your co-Kappa-Simpson equivalence relation. Okay. What you're basically testing is whether these small, low complexity sets are enough to capture your equivalence relation. So whether every equivalence class entirely contains one of these simple sets. Okay. That's what this is checking. Code up the intersection of those simple sets which span multiple equivalence classes. Okay. Intersect all those down. If it's inconsistent, then that means that every equivalence class completely contains one of the simple sets. How many of those simple sets are there? Well, how big is the infinity intercept alpha t? All right, alpha doesn't have to go too far past kappa, that's size kappa. So that's a map from kappa onto your equivalence classes, which is your quotient space. So that gets you into kappa. If that code is consistent, then you can treat gamma as a forcing. It has a partial order. And you can force below that condition. And being below that condition ensures that the generics, which do correspond to real numbers, are E inequivalent. So now you've got this big forcing, it's got all kinds of splitting going on, so you just build a perfect tree inside there. Copy the Cantor set of generics, basically. And they're all E inequivalent, so that embeds R, which is really the Cantor set, into the quotient space. Alright, so that's kind of the gist of it. It's not so bad. Okay, so just to recall, this was the defect in Casado-Ketracid, these little things in red, the imprecision. So we're able to fix that. Okay, start with something that's both kappa and co-Kappa-Suslin, and it's in the universe of determinacy. And inside of that universe, I can either embed it into kappa, embed R into it, and embed it into 2 to the kappa specifically, or R mod equal, embed into it, and these are mutually exclusive choices. All right. And the outline is sort of not so bad either. So now our L actually has T and T prime in it, so it's a slight modification. And you do an approximating equivalence relation where you say X and Y are E tilde invariant if they lie in exactly the same E invariant simple sets. Okay? If those are exactly the same, then every equivalence class basically corresponds to a kappa length binary code of which E invariant sets are you in, and which are you not in, right? So that embeds your equivalence classes into 2 to the kappa. Or rather, embeds R into the kappa in a way that's constant on equivalence classes. If they're different, then that difference is back in the point class. Once again, we force below it. Generics still correspond to reals. Distinct generics are E equivalent. This is all a lot of work that's being shoved under the rug right now. And you build something called a link structure, which is a very fancy kind of binary tree where you kind of nodes are sort of linked together, basically. And this creates a copy of R on Q. I don't really want to get too much into the details on that. Okay, so then that solves it, right? All right, so I think personally the interesting part of this is the tools that I kind of built up to handle all of this, these semantics. Proving this theorem is just kind of like a road test of it, in my opinion. So I have a variety of questions. One, if I go back in the context of Silver's theorem, where they used a signal on one set corresponding to a computable tree, is my gamma the same as that signal on one? My impression is no. I think it's strictly smaller, but it's weird. Okay, so that's just a weird technical question. Two, saying I'm inside of 2 to the kappa is a very broad statement, right? I would love to be able to say more about what kind of subset I am. And hopefully use gamma to do some other kind of diagnostic like we just saw with the proof sketches, to say I'm in this kind of subset of 2 to the kappa as opposed to something else. I know in general that's basically impossible, but maybe there's some things that could be said. And then there's some other dichotomies. You can go past R mod Q into like R to the naturals mod L1, like little L1. There's some other known things that can maybe be extended to, that are only known for Borel currently, but could be extended this way. And then finally, I mentioned before, one version of the proof of Silver's theorem uses those countable collection, these signals on one set as a basis for a topology, and uses category instead of forcing. So you prove that that space is segment countable, non-retrieval, strong show K, and then are able to use category from there. So I'm able to use forcing with gamma, and generics correspond to reals, and lots of nice things happen. So if I shove gamma in as a basis for a topology, okay, now it's like a kappa-sign basis for a topology, can I guarantee some fair category things about it? Is it strong show K? I have no idea. This is just a random question. All right, so thank you for listening, and thanks for yeah.
Can you go back to the statement I'm giving here?
This one, yes.
So you have 2 assumptions on the kappa-Suslin and the co-kappa-Suslin.
Yes.
Do those correspond to different parts of bullets 1 and 2, or do you need both for each of bullet 1 and bullet 2?
So if you were just co-kappa-Suslin, then you get this and the first half of this. And there's these pieces. Being kappa-Suslin and co-kappa-Suslin basically corresponds to being Borel. That's the idea. Okay. Higher level.
Other questions? Okay, let's thank the speaker once again. Next, talking about 7 minutes.
I'll have seconds. All right, folks. I'd like to introduce the last speaker of the special session, Nikolai Krupski. Take it away.
Thank you. I'll speak on a cardinal invariant called functional tightness. This is not a very widely known cardinal function. It was introduced by Arkhangelski to study function spaces. But this talk is not about function spaces. I'd like to advertise this cardinal invariant as an interesting and natural modification of tightness, a very important notion, which is worth investigating, in my opinion. So since this is, as I said, natural modification of the tightness, let me recall the standard notion of the tightness first. I'll do it through so-called kappa closed sets. This is not a standard way of introducing tightness, but there is a reason I'm going to do it in this way. So I will call a subset of a topological space kappa closed, where kappa is an infinite cardinal number if any small subset of this set F has a closure that is inside F. So closures of small subsets are inside. And the tightness of a topological space is a minimal infinite cardinal such that every kappa closed set is closed. So roughly speaking, this cardinal number, the tightness, measures the minimal size of sets determining the topology, because closed sets determine the topology. So one can ask, what if instead of looking at minimal size of sets determining the topology, we look at minimal size of sets determining the continuity of functions? This leads to a definition of functional tightness. So, an analogy, instead of looking at closed sets, I will look at continuous functions, real-valued continuous functions, and I will call a function defined on X from X into the reals kappa continues, where kappa is an infinite cardinal, if this function, when restricted to a small set, it is continuous. So continuity can be tested on small sets. Size of most kappa. So the functional tightness is the minimal cardinal, infinite cardinal number such that every kappa continuous function is continuous. Continuity is tested on small sets. So this is a pretty natural modification of the tightness. But as I said, the main interest in studying this cardinal function comes from the theory of function spaces. And in the theory of function spaces, there is a related notion which is also very important, so let me mention this here. A function is called strictly kappa continuous if not only its restriction to a small set is continuous, but for any small set, there is a continuous extension of this function to the whole space. So this is a stronger notion, and the mini-tightness of the space is the minimal infinite cardinal number such that every strictly kappa continuous function is continuous. This mean tightness is very useful in function spaces, and functional tightness may be a little bit more natural to define. Fortunately for us, those two will coincide because they coincide for any normal space X, and we will be interested in compact Hausdorff spaces. What are the motivations for studying these cardinal functions? They both were introduced by Arkhangelski, who proved in the 80s the following theorem. It it turns out that the Hewitt number of CP space, CP of X, is equal to this mini-tightness of underlying space X. I'm not going to define the Hewitt number here. In particular, this means that CP of X is real compact if and only if the mini-tightness of X is countable. And shortly after Archangelski proved this theorem, Uspensky showed that there is a full duality in the sense of CP theory between Hewitt number and this Carnot function Tm. That is, the Hewitt number of the underlying space X is equal to the mini-tightness of CPX. In particular, X is real compact if and only if CPX has a countable mini-tightness. And in this case, for CP spaces, it turns out that both Carnot functions, mini-tightness and functional tightness, coincide, they're equal. So those Carnot invariants T0 and Tm were introduced by Archangelski, but in fact, the notion of omega continuity, this concept of omega continuity was used much earlier by Corson, who proved that if you have any Banach space, then it is real compact in the weak topology if and only if every linear functional on this Banach space, which is omega continuous in the weak star topology on the dual space, is continuous. So it is almost, it almost says T0 of T0, the functional tightness of the dual space in the weak topology is omega. Here we're not interested in here, we're considering linear functions, however, not arbitrary continuous functions. All right, so, but in this talk, I'm not interested in the theory of function spaces. We have a natural Carnot function. We'd like to study its properties. So first, let us look at some simple properties of this Carnot function. It's obvious that strict kappa continuity implies kappa continuity. And both notions are equivalent if the space is normal. And hence, we have the following inequalities. The mean tightness is always below the functional tightness, and it follows from the definition that the functional tightness is always below the tightness of the space. But not only that, and this is an important feature of functional tightness, it is not only below the tightness of X, but it is also below the density character of the space. Density character is the minimal cardinality of the dense subset. So it is a common refinement of both the tightness and density character. And since strict kappa continuity and kappa continuity are equivalent if the space is normal, the mean tightness and the functional tightness are equal if the space is normal. And in particular, compact Hausdorff, and this will be our set. There is a stronger relationship between the functional tightness and the tightness. Not only the functional tightness is below the tightness, but actually the tightness of any topological space is the supremum over functional tightness of all subspaces. And let me give you this simple example where they are not equal, the tightness and the functional tightness. Consider the Cantor cube of weight omega 1. The tightness of this space is omega 1, but the functional tightness is countable because this cube is separable, and the functional tightness is always below the density character. What are the properties, some simple properties of the functional tightness? There is a sharp contrast between the behavior of functional tightness and the tightness. Namely, the functional tightness is not monotonic with respect to closed subsets. And also, it is good to notice here that the functional tightness is not raised by quotients. And I'm interested in a Cartesian product. So what can we say about Cartesian products and behavior of the tightness under the products? And what I mean by that? Well, in general, if we have any cardinal function, it is reasonable to ask, can we evaluate this cardinal function on the Cartesian product of spaces in terms of the values of this function on all factor spaces and probably the cardinality of the set of indices. Usually, there is no hope for answering this question in the full generality if you don't assume anything about your topological spaces. So very often, you have to assume something about the spaces, and often you consider this question assuming that all factor spaces are compact. And then there is a chance of proving something interesting. What about the tightness and the functional tightness with respect to this question? For the tightness, we have a very good answer. This is a classical theorem of Malihin from the 70s, which says that if you have a family of compact spaces, and there are many of them, and each factory space has tightness bounded by kappa, then the product, the tightness of the product, is also bounded by kappa. And from this theorem, using this theorem, you actually can evaluate precisely the tightness of the product. What about the functional tightness? Well, this is the main question in this talk. Is there a counterpart of Malihin's theorem for functional tightness? This is not my question. This question was posed by Oknev, who studied productive properties of functional tightness. In particular, he was able to show that the functional tightness behaves nicely for finite products. In particular, if you have a product of two compact spaces, then the functional tightness of the product is bounded by the maximum of functional tightness of those two spaces. And if you have it for two spaces, you have it for finitely many. But he was not able to prove, to extend this result for infinite products, and note that Malihin's theorem says something about infinite products. So he posed this question: what about infinite products? Is there a counterpart of Malihin's theorem for functional tightness? In particular, it was not clear, is it true that countable power of a compact space has the same functional tightness as a compact space X? This is true for ordinary tightness, and this follows, for ordinary tightness, this follows from Malihin's theorem. The tightness of the countable product of the compact space is equal to the tightness of the compact space X. Alright, so let me show you answers. It turns out that yes, there is a counterpart of Malihin's theorem for functional tightness. Let me show you two theorems. Consider, so let us fix an infinite cardinal number kappa, and let us consider a family of 2 to the kappa many compact spaces. And assume that the functional tightness of each of them is bounded by kappa. So we have 2 to the kappa many spaces, and kappa is a common bound for functional tightness of all factor spaces. And then it turns out that the functional tightness of this large product is also bounded by kappa. So it is even better than in Malihin's theorem. In Malihin's theorem, you have here the product of kappa many spaces. For functional tightness, you can go to 2 to the kappa many spaces. In particular, not only countable power of a compact space has the same functional tightness as a compact space X, but C power of any compact space has the same functional tightness. And there is another theorem, which is not a generalization of one. It is a different theorem. And in this theorem, we have 2 infinite kernels, kappa and lambda. Lambda measures the size of the family. So we have lambda many compact spaces here. And kappa is a common bound for functional tightness of all factor spaces here. And then we have to assume something about the size of this family. And the assumption is the following. So the assumption is on lambda. If lambda is below the first measurable cardinal, then the functional tightness of the product, perhaps very large product, is also bounded by kappa. In particular, if there are no measurable cardinals, it can happen. The functional tightness product. And you have to assume something. So if lambda is measurable, then this is not true. So this is the best you can get. Let me mention something about the proofs, how we can get results like that. So the main idea here is to look not at the full product, but certain subsets of the product. And the good notion here is so-called sigma product. What is a sigma product? This is a very good concept. So you fix a basic point. This is A. A is an element of the product. And the sigma product base at this A is the collection, is a subset of the product consisting of all elements of the product that differs from A on the finite set of coordinates. They are, sigma products are sufficiently simple to work with, but also, on the other hand, sufficiently complicated to tell you something interesting about the product. In particular, they're dense. We need this definition. A function defined on the product of topological spaces will be called sigma continuous if its restriction to any sigma product is continuous. And I will call it 2 continuous if its restriction to any copy of the Cantor cube inside the product is continuous. And why I use these notions? Because there is following a whole theorem of Noble from the 70s. If you have, it says that if you have a function defined on the product that is both sigma continuous and 2 continuous, then it must be continuous. So to check continuity, when your function is defined on the product, you must check it on simpler subspaces, on sigma products and copies of Cantor cubes. We will use this theorem, and how we can use it. Say we want to prove this theorem 1, where we have 2 to the kappa many factor spaces, and the functional tightness of each of them is bounded by kappa. We would like to show that the functional tightness of the whole product is also bounded by kappa. What do we have to show? We have to show that the functional tightness of this product is bounded by kappa. So by definition, we need to take any kappa continuous function and check that it is continuous. So let us take arbitrary real valued kappa continuous function. And to verify that it is continuous, we will use Noble's theorem. And this Noble's theorem reduces our task to verify sigma continuity and 2 continuity. And then we will get continuity if we are able to do it. So we have 2 lambdas. The first one says that your kappa continuous function is 2 continuous. So we fix infinite cardinal number. We have the family, large family of compact spaces, 2 to the kappa many of them. And let us take any kappa continuous function. The lemma says it is 2 continues. In this lemma, I need to assume something about the size of the family. I need 2 to the kappa many spaces. And the proof is very simple. Let me show you. Just fix a copy of the Cantor cube. To verify kappa continuity, I need to take arbitrary copy of the Cantor cube and check that the restriction of my function to this Cantor cube is continuous. So let's take this y copy of the Cantor cube as this form. So this is a product of y alphas. Each factor space y alpha has at most 2 points. But look, Hewitt Marcheski-Pondicherry theorem says that the density character of this y, since I assume that the size of the family is 2 to the kappa, the density character of y is bounded by kappa. And functional tightness is below the density character. And now your function f is kappa continuous, so its restriction to y is also kappa continuous. T0 y is below the density character, it is below kappa, so any kappa continuous function on y is continuous. And hence you have 2 continuity. Your function restricted to y is continuous. And lemma 2 says that any kappa continuous function is sigma continuous defined in the product. So it says that if you have a family, and here I can assume that this family for sigma continuity is this family of spaces can be arbitrarily large. In fact, if I have arbitrary family of compact spaces, and functional tightness of each factor space is bounded by kappa, then any kappa continuous function defined on the product is sigma continuous. Here in this lemma, I don't have to assume anything about the size of the family. I need to assume something to get 2 continuity. What about measurable kernels? There is this other theorem about involving measurable kernels. Instead of the lemma 1, I can use the following proposition proof by Uspensky, who showed in fact, he was able to evaluate the functional tightness of the Cantor cubes. It turns out that if kappa is below the first measurable kernel, then any omega continuous function defined in the Cantor cube of weight kappa is continuous. Using this proposition instead of lemma 1, I'm able to get this result for involving measurable kernels, theorem 2. And measurable kernels here, you must assume something about the size of this family because of this example. If lambda is measurable, in other words, if you have a 2-valued non-trivial measure on the Cantor cube, then this measure defines a function. And this function, it can be proved, it is not very difficult, that this function is omega continuous, but it's not continuous. So this gives you that the functional tightness of this cube, this above omega is uncountable, although each factor space has, of course, countable functional tightness, so it is unproductive. Thank you for your attention.
We have time for maybe a quick question.
I didn't understand the very last example. How is mu a function?
Oh, instead of so you have a set, just look at the characteristic function.
Okay. Sorry. Any other quick questions? The plenary talk starts in about 12 minutes in the building next door. So thank you guys very much for being in the special session.